Yesterday we started talking about exponential functions and more specifically about exponential growth functions. And today I want to continue talking about the discussion, and more specifically I want to talk about how those exponential growth functions apply to our real life, both with models that include exponentials as well as something called compound interest, which every one of you should be interested in as you think about bank accounts and how to make money in the future. Before we do that, however, I want to review a little bit what we talked about yesterday. More specifically, I want to talk about the growth model, which is y equals a b to the x. And more specifically, this isn't even the growth model. This is every exponential function. It's a growth model if that b is bigger than 1. We talked a lot about kind of how to graph the thing. We should know that the parent function, okay, the parent function should always look like the form y equals 2 to the x, or y equals 3 to the x, or y equals 4 to the x, whatever it might be. If I look at all those, there's a lot of different parent functions for these different kinds of exponential growth models, okay, but every one of them has a parent function, and then you can go ahead and transform them left, right, up, down, flip, or whatever it might be based on whatever you're given. So if you were to look at this, if I call this kind of the blue line, if I call this the green line, and I call this one the red line, we should also know that if I were to graph each one of these, okay, here's my nice XY axis here. I know that if I graph y equals 2 to the x, again, I'm approximating a little bit. I'll say this is at 0, 1. Okay, if I do something like this, okay, this is kind of my nice y equals 2 to the x exponential function. I know that if that number is the base, that b value, okay, is bigger, it gets bigger and bigger and bigger, I know my curve is going to get sharper and sharper and sharper. So again, here's my green. So this is going to be represent y equals 3 to the x. I'm getting a little bit sharper. In both cases, they still approach 0 to the left. And then similarly for y equals 4 to x, okay, it's going to be even a little bit sharper. It's still going to go ahead and approach 0. Okay, now if you look at this, you can see that the bigger that value is as the base value, the sharper the curve should be. And that makes sense because if you're taking a bigger value to a power, it's going to get the result's going to be that much higher every single time that you increase it. 2 squared is certainly not as big as 3 squared or 4 squared. 2 cubed is certainly not as big as 3 cubed or 4 cubed. So that curve should be that much more sharp the bigger that number gets. We also talked about transformations, not only just the parent functions, how to graph them. Okay, we also talked about what happens if I have something like, I don't know, y equals 1/2 times 3 to the x minus 4 plus 5. Okay, we should know every single time what every piece of this function does. For example, we should know that this minus 4 right here, it's inside the function, so I think this moves left 4. Okay, this one right here, this plus 5 on the outside, isn't affected by the power, so I know I'm going to take the result of whatever that power gives me, and I'm going to add 5 to it. So in other words, I'm going to move it up 5. Things on the outside, move it up and down, or numbers on the outside, move it up and down. And then finally, this up front, this 1/2, we know it's simply a multiplier. And what I mean by multiplier is whatever you get as a result, after you've moved it left, right, up, down, okay, now I'm going to multiply that quantity by 1/2. So if something less than 1, it's gonna cause that curve to take longer to get going because I'm multiplying every one of my results by 1/2 or taking 1/2 of it. If it happened to be something bigger than 1, like if it was a 2 or a 3, I'm going to take that result and multiply it by 2 or 3, so it's going to make it go faster and make that curve even more sharp than it already is. So it's simply a multiplier. That leading coefficient is a numerical value that you're going to multiply your result by to see what's going on with that new function. With all that in mind, okay, I want to go a step further. We have the base idea of what it looks like to actually graph something, okay, but now what happens when we actually apply it to real life? That's what 7.1 Day 2 is about. Exponential growth, and more specifically, compound interest. First things first. There's a lot of writing on this page. Okay, it talks about exponential growth models. So what if I have a situation that's actually showing some sort of patterns of exponential growth? It's growing rapidly, and I think an exponential model might fit that. So it says this: when a real life quantity increases by a fixed percent each year. So think about something that actually increases by a fixed percent each year. Increases by 4%. Obviously, the first thing I think about is bank accounts. Okay, the amount Y of the quantity after t years can be modeled by the equation. So already you can see this. It's y in terms of t. So if you look at this, and I'm going to be drawn all over the page here, okay, I have this variable, y in terms of t, Immediately that tells me that A is going to be a numerical value and R is going to be a numerical value. Okay, it's just going to change based on the situation that you're in. So here's my two variables, Y and T. So Y is the amount basically after T years. So right underneath it says this. It says A is the initial amount. Okay, so if you think about a bank account, you throw $500 in there right away to kind of start the bank account. There's your initial amount. Okay, and it also says this, R is the percent increase. Okay, R is the percent increase. Okay, and what's big is that R always is expressed as a decimal. So if it's a 4% rate increase or some kind of 4% increase, that's going to be 0.04. It's going to be the decimal equivalent of that percentage that they give to you. So now, you might ask yourself, how does this relate to the exponential growth function? Well, think about it. If this is the case, my exponential growth function from yesterday was y equals ab to the x. If I wanted something to grow, I needed b to be bigger than 1. So if you look at this, if you look at the growth model, I have 1 plus r sitting right there. I think that relates directly to b. We're taking 1 plus r to some value that we call t. In our generic model, we took b to some generic value that we call x. In this case, we want it bigger than 1. We're going to have a rate that's a percent increase, so it's going to be bigger than 1. So when I have 1 plus the rate, or 1 plus some sort of decimal, that's going to be bigger than 1, therefore creating a growth model. So for example, if my rate was 4%, I put 0.04 in there. 1 plus 0.04 is 1.04, and bigger than 1, I'm going to have a growth model. Also, A is my initial amount. A stays the same. So if you look at the growth model compared to our basic from yesterday, okay, A is A. A is our initial amount. It is our multiplier. What do we start with? What are we gonna start with in order to start multiplying this growth factor by? And then T, again, stays the same as the number of years that this percentage, this growth is going by until we decide to take the money out, or whatever we're growing by, population or money or whatever it might be. So let's go take a look, for example. It says in 1970, the population of Kern County, California was about 330,000. From 1970 to 2000, the county population grew at an average rate of about 2.4%. What I want you to do in number 1 is write an exponential growth model given the population P of Kern County T years after 1970. So initially what I want to do is I kind of want to take a look at it and say, okay, I know that I have T years from 1970. So if I think about 1970 being T equals 0, that's the first, that's an initial year that we started. And I think I have some information here. If I start with my generic model, if I start with Y equals the generic model from the previous page. If I go back there, I say Y equals A times 1 plus R to the T. Let's plug in what we know. First of all, we know that we want to leave two variables in there. From the previous slide, we know we want Y in terms of T. In this case, we're actually going to go ahead and gear a little bit towards the population of the problem. It says, write an exponential growth model given the population P of Kern County after T years. So Y is usually my output. In this case, I want P to be my output, my population to be after T years. And then you got to start looking. Okay, A, it's my initial amount. What's my initial amount? What was the population in 1970? If I go back to my problem, I see that my initial amount was 330,000. So I plug that in, 330,000 times 1 plus my rate. So 1 plus my rate, my average rate over those many years is 2.4%, and I know 2.4% of the decimal is 0.024, all raised to the T. Now, obviously, we can go ahead and abbreviate this at least a little bit. We can go ahead and reduce what's on the inside there. And so if I cheat a little bit and I go over to the little bit open space, I think my model is going to be population equals 330,000 times 1 plus 0.024 should be 1.024, all raised to the T value. I think that this is going to be my exponential growth model for those 30 years in Kern County. Number 2 says about how many people lived in Kern County in 1990. Well, the first attack is going to be, okay, I have my model. My model is from the previous one, 330,000 times 1.024, all raised to the T. But now the thing is, I want to find my population. In other words, I want to find P. That means I need to know what t is. Well, in this case, it says I want to know my time is going to be 1990. Okay, so I got to think to myself, okay, I know that 1970 was t equals 0. So if I put that, I know that 1970 was when t is equal to 0. So if that's the case, I know 1990 has got to be when t was equal to 20 years later. So if I plug that into my function, I have population equals 330,000 times 1.024 all raised to the 20. And if you want to take out your calculator, I'm going to do exactly the same thing. Go ahead and type in your calculator, 330,000 times 1.024 all raised to the 20th power. I get a value of 530,200 and I'm going to round that last one, so 290 people. Okay, so I know 20 years later it's increased to that. Go ahead and make sure that you can get the same thing on your calculator, please. Another piece of exponential growth, and one of the most common applications of it, is what we call compound interest. Okay, you may have heard that before. If you have some money in the bank, you might have heard about compound interest. Okay, it's worth your time to know what that means. It's worth your time to kind of be able to understand what that means when they say it's going to compound monthly or compound annually or compound, continuously. It's nice to know that so that you can go ahead and make the most money that you can so the bank can make you some money. So if you look at this, it says exponential growth functions are used in real life situation involving compound interest. Compound interest is interest paid on initial investment. So again, think about that bank account. You throw in $500 in, okay, and they said, okay, every single month or every day or every year, we're going to go ahead and give you a certain percentage on top of that. So if you leave it in for a year and you gain 4%, okay, you're going to earn 4% back on that initial amount of 500, and that's going to be also in your bank account. It's free money that the bank has given you for keeping your money in their bank. Okay. The second sentence says, compound interest is interest paid on the initial investment, called the principal. So the initial amount, okay, we're no longer going to use initial amount. Now we're going to call it principal. Okay, that's a good word to know. And on previously earned interest. Okay, so compound interest is going to go ahead and collecting on whatever's in the bank account at that time. Okay, interest paid only on the principal. Principal is called simple interest, and we'll talk about kind of the difference between those tomorrow in class. Compound interest, I'm on the second box. It says this, consider an initial amount, P, deposited in an account that pays an interest at an annual rate. Again, notice that the rate needs to be expressed as a decimal. That's big. So if it's 4%, we want to go ahead and plug it in as 0.04. Compounded so many times a year. Okay, that so many times a year is what we're going to call N. Okay, and we'll talk about what that means. But if I want to talk about compounding certain times of year, okay, we have to figure out kind of a lot of different words like bi-monthly, bi-weekly, whatever it might be. We got to make sure we know what that means. But notice it's always compounded per year. Okay, so how many times per year are we compounding that? And that's the numerical value you're going to plug in for N. And it says this, the amount A in the account after T years is given by this equation. So every year I do this. Okay, I always kind of break this down because there's a lot of words on this page. It's nice to be able to break it down. Okay, first of all, make sure you focus on this equation. This is what ultimately you need to know, along with the one from the previous page. If you want to do compound interest, you want to be able to do this. First, A is going to be the amount after T years. P, just like the previous problem, is going to be your initial amount, but now we've changed it to what we call the principal, and I'll also put initial amount in there. What are you starting with? What are you putting in your bank account to start? Okay, there's your initial amount. Okay, again, here's your, right here, I'm not going to go ahead and necessarily label it, but this little spot right here is your growth factor. How much you're growing by. It's going to be 1 plus something because you want something to grow and you want something bigger than 1, so it's going to be always 1 plus something. Okay, first of all, if I get rid of that red line so I can go ahead and talk about the things on the inside. If I took a look at that R is my rate. So if I take a look at this, kind of bring it down over here, and I'll change colors. I don't think you can see it red all that well. If I talk about R is my rate. Okay, at what percentage am I increasing by? Okay, now N is the one that's tricky. N is how many times R happens a year. And what I mean by that is, if I want to earn 4% annually, I know that that rate's only going to happen once a year because annual means once. But if I say monthly, and if I want to go ahead and gain interest on a monthly basis, I know that rate of 4% is going to go ahead and happen 12 times. Why? Because monthly, there's 12 times that happens in a year. And then similarly, the one that we already know, the only one that we haven't defined yet is T, and T is going to be the number of years that this is happening. So if you keep that money in your bank account for all 18 years or whatever, 18 years of your life before you go off to college or whatever it is, okay, that would be represented as T. So before we actually go ahead and try and do a problem, let's try and actually make sure we define a couple of these things. Okay, with N being the number of times a quantity is compounded a year. So N is the number of times that rate is actually being applied to your account every single year. You have to know the difference between a lot of these numbers, okay, or a lot of these words, rather. If you look at this, I have annual, okay? Annual has to mean, if I'm talking about annually, okay, that means how many times per year? Annual means one time a year, so once, 1 year, okay? If I look at semi means two, okay? Semi-annually means twice per year. If I look at quarterly, okay, quarter, like a 25 cents, quarter means 4 times a year. If I look at monthly, hopefully there's 12 months in a year, so I'm talking about 12 times in 1 year. If I look at weekly, okay, I think there are 52 weeks in our year, so I'm talking about that rate happening 52 times over the course of 1 year. If I look at bi-weekly, kind of like semi-annually was twice a year, bi-weekly means every 2 weeks. Okay, and so if I think about the fact that I have 52 weeks in 1 year, if I do it every 2 weeks versus every week, I think that's going to be 26 times a year. And how am I getting that? I'm taking 52 weeks, dividing it by 2 to get 26. And then daily, assuming not a non-leap year day, okay, we can assume, unless they tell us otherwise, that we're going to go ahead and apply that compound interest 365 times a year because there are 365 days in a year. So let's try and do this. If I take a look at this one right here, if I take a look, it says you deposit $5,500 in an account that pays 3.6% annual interest. So stop right there for a second. Start identifying stuff as you go. It says you deposit $5,500 in an account. I'm starting with that. So I think right there is my initial amount. So immediately I kind of go, hey, I know something right here. Okay, this right here is going to be something. It's going to be some sort of initial amount. Okay, but then it says this, 3.6 annual interest. Okay, obviously the 3.6 is important because that tells me the rate at which I'm gaining interest. Okay, but even probably more important is the fact that I know that this is an annual interest. If it's an annual interest, okay, I know that this 3.6 is only going to be applied to my account only once a year, okay, because it's annual. So what I want to do is I want to find the balance after 2 years. So right there again is another key piece. How long am I keeping this in my account? I'm keeping it there for 2 years. If the interest is compounded with the given frequency. Okay, so immediately I know, okay, it's an annual interest. Okay, so I know I'm going to get it every single year. But what if I change it? Okay, what if I change it? What if I change it, for example, to semi-annual? As a matter of fact, let's go ahead and do 3 of them. Let's do this over here. If I want to keep it as an annual interest, okay, if I want to keep it only as an annual interest, I want to see how much I keep. So let's go ahead and write down the formula. Y equals, I have P, instead of using Y, I think from the previous page they start using A for amount, so I'm going to use A equals P times 1 plus R over N, 1 plus R over N, all to the NT. So if I look at this, I want to know my amount after 2 years, so I'm going to keep A the same, that's what I'm trying to find. I know my initial amount is 5,500 times 1 plus my rate. My rate is 0.036. 3.6% is a decimal. Now I'm only going to do that once a year. So initially it tells me I'm going to do this annual interest only once a year. And I'm again, n is the same. So 1 times the number of years I'm doing this, I'm doing it for 2 years. So again, take out your calculator. Make sure you can actually get the same thing I can. So make sure I'm going to keep 5,500 times a quantity, parenthesis, 1 plus. I'm going to put this fraction also in another parenthesis, set of parentheses, just to make sure I can do it correctly. So 1 plus parenthesis, 0.036 divided by 1, parenthesis, all raised to the essentially second power, because 1 times 2 is 2. So if I look at that, I think after 2 years, I will have gained, or I will have an account value of $5,903.13 if I were to round it. Okay, that's if I only compound the interest every single year and nothing more than that, just once a year for 2 years. Okay, now what if I were to change that? What if I say, okay, instead of me doing it just annually, what if I do it semi-annually instead? Okay, from the previous page, I know semi-annually means it happens twice a year, okay, versus just once, so I know I'm going to do it twice a year. So let's do exactly the same thing. I want to do the same amount, so I'm going to do amount equals, or A equals, my initial amount still is 5,500 times the value 1 plus, still the same rate, still at 0.036, divided by my n value. In this case, I'm not doing it annually anymore. I've changed that in this problem to say now semi-annually. So I know it's going to be changed to 2 because it happens twice a year. And then my n is still 2, still leaving it in there for 2 years, so my t value is 2. So when I plug that in, take out your calculator and see what you get. So if I do 5,500 times a quantity 1 plus quantity 0.036 divided by 2 this time, all raised to the 2 times 2 or 4th, I think I get an amount of $5,906.82. Compare the two values. If I look at this, what's better? Okay, if I look at this, if the bank comes to me and says, Mr. Wall or Tim or whoever it is, what would you rather? Would you rather go ahead and compound this thing annually or compound it semi-annually? Well, in this case, even though it's a small difference, only after 2 years, it looks like I've gained at least $3 more by doing it semi-annually versus actually just only doing it annually. Okay, well, let's go ahead and change it one more time. What if I do it monthly? Instead of once a year for annually, instead of doing it twice a year for semi-annually, what if I do it monthly instead? Same thing, same process. The only thing different now is monthly implies that my n value, which is how many times I'm compounding the interest every single year, it now becomes 12 because it's going to happen 12 times a year because it's monthly. So again, let's do it one more time. The amount equals 5,500 times 1 plus, my rate still is 3.6%, so 0.036 is a decimal. But now my n, I'm doing it 12 times a year, so I divide by 12. The n value is still the same, so 12 times the years I'm doing this, I'm doing it for 2 years. One more time, plug it into your calculator. I'm going to do 5,550. It's going to be 5,500 times the quantity 1 plus the quantity 0.036 divided by 12, all raised to the 12 times 2, which is really the 24th power. And now all of a sudden I'm at $5,909.97. So now all of a sudden, if instead of doing it once a year or even twice a year, now I'm compounding that interest every single month. And you can see there that I've gained yet another roughly $3 on the semi-annual. So think about it. The more often you do a compound interest on something, the more money you get. And the reason why that is because you're going ahead and finding interest. You're getting a percentage of that account multiple times as you go versus just doing it once a year and only getting just a 1 lump sum or two lump sums. You're doing a lot all the time, and you're going to gain more money as a result of it. In summary, you should take away 2 formulas or 2 functions that relate directly to exponential growth functions. The first being the growth model that we learn for any kind of exponential growth model, where y is the output or the growth after t years, A is still that initial amount, whether it be a bank account or a population, whatever it is. What did you start with is my A value, and my R is the rate at which it increases. We did the Kern County population from 1970 to 2000, talking about the rate growing at a certain percentage. This is what you would use in that situation where A is the initial amount, R is your rate at which it's increasing, and T is your for how long, how many years are you actually increasing by. And the next one, the one we just got done with, compound interest. A is your amount after T years. Those are your two variables, just like Y and T were your variables in the growth model. A and T are your variables in the compound interest model. But you know that P, again, is your initial amount. Notice that A and P in both of those situations are both in red, are in the same position. P, in this case, is called principal. Your principal is your initial amount that you start with. R is still that expression as a decimal of the rate at which you're increasing by. What are you compounding by? Is it 4%, 5%, 2.3%? That is your percentage that you're increasing or growing by, expressed as a decimal. And then N is the tricky one, and N is how many times a year. And that's the biggest thing. How many times a year are you going ahead and applying this compound interest to your account? So yes, these are both things that I would expect that you know by heart. We'll talk more about them tomorrow in class. I hope you have a good night. I will see you tomorrow. See ya.